Alright, so we're going to look at College Algebra, Section 2.7, which is analyzing graphs of functions and piecewise defined functions. There's also a lot of other things we'll talk about in this section. We're going to test for symmetry, show you how to do that, identify even and odd functions, graph these piecewise defined functions, investigate increasing, decreasing, and constant behavior of a function. This is really very easy, so don't let this be hard, that objective 4. And determine relative minima and maxima of a function. That's also really pretty easy. The hardest piece of this is probably the first two objectives. I am also going to put some videos online and some animations that come with the book and are produced by the publishers of the book. They're very short, 2 to 3 minutes. Probably worth you taking the time to look at, especially for the first 3 objectives. I think you might need those to help you understand those first 3 objectives. So looking at objective 1, if we have tests for symmetry, if it can be a mirror image over the y-axis, that means it's symmetric with respect to the y-axis. If you replace your x with a negative x, and after you simplify, get the same exact equation you had to start with, then it's symmetric about the y-axis. If you replace y with negative y and get the same exact answer after you simplify, then it's symmetric about the x-axis, or a reflection. You could think of it as could be reflected back and forth over the x-axis. If it's symmetric with the origin, you replace both things, and if you get the same equation, it's symmetric with the origin, which is basically an x-axis and a y-axis reflection. You're going kind of diagonally. So let's look at some of these on these slides. So we're looking at y equals x cubed. That is our original equation that we're going to look at right here. We want everything to be equal to that when we're done, if it's symmetric. So we first replace our x with a negative x, and so we can see we've got this negative x in here instead of x. When we evaluate that, negative x times negative x times negative x is negative x cubed. So it'll be a negative. And so this is not the same. So no, it's not a y-axis symmetry. X-axis, if you replace the negative y, a y with negative y, so this time we're replacing this, making that negative. But then we multiply through by negative 1, so we have y equals negative x cubed. Again, this does not match. This does not match our original equation, so no, it's not symmetric about the x-axis either. But if we do both things and then multiply by negative 1, now here we could say that simplified this, we would have multiplying everything by negative 1. After we evaluate, take away the parentheses, we have negative y equals negative x cubed. Okay. And so that would be then, when I multiply by negative 1 all the way across, y equals x cubed. This one does match. Okay. So, yes, this matches the same thing we had there. So, yes, it is symmetric about the origin, not about the x-axis or the y-axis. Okay. Here's another example. We have x squared plus 5. Again, for y-axis symmetry, you replace x with negative x. If we do that, we see, here's our replacement that we put in. Negative x times negative x is positive x squared plus 5. So again, we're looking for it to match this. And it does. So it's, yes, it's symmetric about the y-axis. We would expect a parabola, unless it's shifted left or right, which this one's not. This one's just simply shifted up 5 to be symmetric about the y-axis. X-axis reflection, again, you're going to replace this, put this negative in front of your y. And so you're going to multiply through now by -1, which will give you negative x squared minus 5, which is not the same as our original, so no, it's not symmetric about x. If we do both things, we have y equals, again, let me go through here, and here we're going to have, when we take away the parentheses, we have we have negative y equals positive x squared plus 5, and we're going to multiply everything by -1, so we end up with just a y, a positive y. So that's going to be negative x squared minus 5, and so no, that's not symmetric. So the only symmetry this has is y-axis symmetry. Another example, this is actually the example of a circle with a center at 0 and -1 and a radius of 2. We didn't study circles, so you all don't necessarily know that. But you can still check for symmetry not knowing that. Again, for our y-axis, we put in a negative x, and we square it, so we get positive x squared, and it's exactly the same as the original equation. So we're looking for this to match. It matches, so yes, it has y-axis symmetry. X-axis, you replace the y with negative y, so that's our replacement. And this, if I multiply this out, and you may or may not want to do that, but if you multiply this out here, your y plus 1 squared will be y squared plus 2y plus 1. If we have negative y, or really let's rewrite that as 1 minus y squared, you're going to have 1 minus 2y plus y squared, which we can see it's not the same because this is a negative 2y and this is a positive 2y. And so that's not the same. So no, it doesn't have x-axis reflection. And again, this one matches, if we check both of them and we replace both the negative x and the negative y, this matches, but this again does not. So it's not symmetric about the origin either. So it is just this particular example just has y-axis reflection. Now we have an absolute value of x plus 2, or x minus 2. So if we replace x with negative x, the absolute value of negative x is the same as the absolute value of x. So yes, that is the same. We're comparing it again back to our original. So yes, it has y-axis reflection. This is an absolute value graph, remember, is a V, and this one is shifted down too, so it's still sitting on the y-axis. X-axis reflection, we put a negative, we replace y with negative y, which when I multiply by -1, that puts this negative out in front here and changes our 2 to positive 2, so no, it's not the same. And with origin, we replace both of them and then multiply through by -1 to get rid of this 1 in front of the negative in front of the y. And no, it is not origin symmetry either. Alright, so even and odd functions are very similar to the test for symmetry functions. As you're testing for symmetry, you can also determine whether a function is even or odd. An even function is symmetric about the y-axis. So that's replacing x with negative x. So once you do that, if you get a y-axis reflection, it's an even function. An odd function is symmetric to the origin. So if you replace x with negative x and y with negative y, and you get your symmetry, then it is an odd function. So determine if the function is even, odd, or neither. We have x to the 4th minus x squared plus 2. So remember, we're looking to see, make sure that it matches with that when we're done with our substitution. So we're going to replace all our x's with negative x's. And anything with an even integer for an exponent is going to turn back positive. So we have x to the fourth minus x squared plus 2. That means that it's exactly the same as our original function. So therefore, this little set of 3 dots means therefore it is even. Determine if the function is even, odd, or neither. Okay, again, replacing x with negative x, all of our x's. We end up with negative x cubed plus x plus 3. Not the same as our original function. We're shooting for it to look exactly like this. So it's not even. Is it odd? We make a negative y. Remember, this is basically, this is negative y here. So multiply through everything by negative, so that makes this a negative and changes this to a positive and makes this a negative, which is not the same as our original function. So it's not odd either, it's neither. Can be neither. That's going to be an answer. Okay. Now this one's a little crazy the way they've written it, so let's talk about this. We're going to replace x with negative x. Okay. We get negative x cubed. That should be a negative. That's a wrong. Should be negative x cubed plus x. It is not even. I think they meant to write minus even means not even. So it's not even. It didn't match exactly. It's got to be, remember, it's got to look exactly like this to be the same. Now we're going to replace, this is going to be negative y, negative f of x. So I'm going to write negative y equals, just because I like that better, negative y equals, and, well, for odd we replace both. But we already have the f of negative x. So, this is our f of negative x. Negative y is going to be negative x cubed plus x, which does match. So f of negative x, let me go back. Okay, negative f of x, which is the same as negative y, is equal to f of negative x. So these come out to be the same. So what matches here are, to be an odd function, this matches this. This one doesn't check back with the original for an odd function. Your f of negative x and your negative f of x should be equal, and then it is an odd function. Alright, if you have a graph, remember you just look for y-axis symmetry or origin symmetry. Here's this y is a kind of a mirror image line. You can see that it's reflection over the y, so it's an even function. And if I reflected it over the x and then again over the y, or the y and then the x, or kind of diagonally up, then it's an odd function. This is origin symmetry. Again, you're looking for origin symmetry. Okay. And now we're going to move on to piecewise defined functions. Piecewise defined functions are functions that are evaluated at different domains. So for all of our x's less than 0, we'll use x squared plus 1. So that's a quadratic, and it has a y-intercept of 1. So that's this graph right here. Okay, that's that graph right there. And you notice here it's an open circle because of this. This does not have a line under it. But our 0 is included in the domain with this second function, x minus 1, which is a line that has a y-intercept of -1 and has a slope of 1. Okay, and it goes from 0 to infinity. So really there should be an arrow here. And there should be an arrow here if you were really drawing it for all x's less than 0. But we're just evaluating this graph. They've already graphed it for you. For f of -1, we're looking here. So we're going to use this first graph. And so we're going to put in -1 squared plus 1, which is 2. For f of 0, remember we don't use this first line, we use the second line. So we're going to use this one, which is 0 minus 1, or -1. And so we can see at f of 0, if I look at the graph, it doesn't include the positive 1, but it does include the -1. For 5, again, that's bigger than 0, so we'll use 5 minus 1, or 4. And so we can check, for x equals 5, we should be at 4, and we are. Okay. So now we've got 3 equations, and we don't have a graph to help us. So let's figure it out. For h of 1, that's less than 2, so we're going to use x squared plus 3. So we have 1 squared plus 3, which is 4. For h of 3, well, 3 is between 2 and 4, so that value is going to just be 7. There's no equation there, it's just 7. For 4, we have a 4 in 2 places, so which one do we use? This is the one that includes the 4 because it's got the line underneath the inequality. So it's for all x's between 2 and 4, including 2 and 4, so that answer is going to be 7 also. And then for all the x's greater than 4, which 5 is greater than 4, we'll say 2 times x, or 2 times 5 minus 1, which is 10 minus 1, or 9. So that's how you're going to evaluate this type of piecewise function. And again, there's a video online that talks about this. All right, so let's look at these real quickly. -3 is less than -2, so we'll say -3 plus 7. So A is going to be 4. F of -3 equals 4. For B, we've got -2. Well, -2 is in 2 places, but it's the second one that includes the -2. It's got less than or equal to -2, so it's going to be -2 squared, which is 4. So f of -2 equals 4. So f of 1, again, we've got 1 in 2 different places. This is the one that includes the 1, so that's just going to be 3. And f of 4 is also included in that last equation, so that's also going to be 3. All right, so what if we want to graph these functions? We have 2 lines here, and again, there's an animation on that you really ought to watch for graphing. So we have 1/2 x plus 1, and so we put our y-intercept here. We have a slope of 1/2. Positive 1/2, up 1 over 2. You know, you would graph it. Normally you would just keep going up here, but we don't need it for this part of the domain. We only need it for all x's less than 2. So you erase the part you don't need. Okay? And so it doesn't include 2, so we have the open circle here at the end. And then we draw our line through these points. Now this point is not right. This should be 1/2 times 2 is 1, and 1 plus 1 is 2. So that actually should be the point 2, 2. For every x greater than or equal to 2, we use the at -x minus 1. So if we has a slope of 1. If we continued this up, you know, it would go like this if we kept drawing this line. But we don't need it for these. We only need it from 1 to, for all x's greater than 2. So we erase the part we don't need. And this, the top graph is for everything less than 2. And the bottom graph is everything 2 and greater. It includes the 2, so we're sure to put the closed circle in there at the 2. Okay? So that's how you would graph this piecewise defined function. You have to graph the pieces. So here's another one with 3 different equations. For x is less than 0, we're a flat line at -1. Okay. From 0 to 2 inclusive, so we have, this was actually left out in the first one, but it was included in the second one. So there's the dot just kind of overrides that empty circle. And then so from 0 to 2, we're x minus 1, y-intercept of 1, a slope of 1. And then for x is greater than 2, we have, if we continued this on up, you know, we'd have here our y-intercept of 6 and a slope of -2. But again, we don't need that part of the graph. We only need the part from 2 to infinity. And so that's the part that we draw. Now this end point here, that 2 is going to be an open circle because there's no line underneath that inequality. 2 is included with the middle portion, but not with the this bottom line. And so that would graph that piecewise function defined by these 3 equations on these 3 intervals. But this is just an example of a word problem that might involve piecewise functions. A new job offer in sales promises a base salary of $3,000 a month. Once the salesperson reaches $50,000 in total sales, he gets that base salary plus a commission on sales over $50,000, or including $50,000. So write a piecewise defined function in dollars to model the expected total monthly salary. So he's going to make $3,000 for 0 to 50,000. Okay, including 0, not including 50,000, because the 50,000 he can get commission on. It says up $50,000 or more he can get commission. So the $50,000 is going to be included in the equation where he gets commission. So 3,000 plus 0.043 for everything. This is what he say made 60,000. He would get paid commission on $10,000. X minus 50,000. And this is for all x is greater than or equal to $50,000. So 50,000 plus in sales means salary plus commission. And so that's how you could draw, if you wanted to make your own graph, if you were making money, you wanted to kind of make your own graph of how much you should make, you could do that. So investigate increasing, decreasing, and constant behavior of a function. Excuse me. This is actually really easy. Increasing means it's going up. Decreasing means it's going down. Constant means it's a flat line. You always look from left to right, just like you're reading a book, from left to right. So if you have this graph, increasing, you can see it's going up from here, and you always read your x's. So from -5, or actually this is negative infinity because there's an arrow, to -2. From negative infinity to -2, you're increasing, and then you're increasing again from 2, and with an arrow there it's to infinity, all the way this way. Okay? This is negative infinity here, and you're going from left to right. So from negative infinity to -2, and from 2 to infinity, it's increasing. Now the only thing I think these intervals are always with curved brackets. I believe in the video that's on there, they put square brackets. So be sure to discover in your homework online. I think it'll want curved brackets. But, you know, you can do what you need to do to get the right answer. So we notice we're decreasing here, going down from 0 to 2. This part is where it's decreasing. So that would be our interval from 0 to 2. And it's flat here from -2 to 0. It's going to be flat in this section between that domain. And again, you're listing your x values. It's the domain over which the interval is in the function is increasing, decreasing, or constant. Okay. So looking at this one, is it ever going up? No, it's never going up. As I read from left to right, it's always going down. So it's never increasing. It's always decreasing. So it's negative infinity to positive infinity, because sometimes you'll have an endpoint to deal with, but these have arrows. And then constant, it's never constant either. It's never completely flat. So it's always decreasing, this particular function. So looking at this, where is it increasing? Okay, this one has an endpoint at -5. So it's increasing from -5 to -3. And it's also increasing, we got a union, put the union symbol there, from -1 to 2. Okay? Those are the places from left to right that it's going up. B, it's decreasing from 2, and that looks like an arrow, so it'd be 2 to infinity. And it's constant from -3 to -1. And so that's all there is to increasing, decreasing, constant. You just look at the graph. Where is it going up? Where is it going down? And where is it flat? Relative minima and maxima of a function. So relative minima and maxima are just the hills and valleys of the function. This is a relative maxima for some small interval. It's not the maxima for the whole curve, maybe, but it's the relative maxima for this small interval. This is a relative minima for this small interval, excuse me. And so the way you would look at this, the point, here's a graph, the point -2, -1, which is right here, is the lowest point on a small interval surrounding x equals -2. At x equals -2, the function has a minimum of -1. So this will be your y value here. Okay. If we look at the same graph, the point 0, 1 is the highest point in the small interval surrounding x equals 0. At x equals 0, the function has a relative maxima of 1. Maxima is the hill, minima is the valley. Okay. Identify the location and value of any relative maxima or minima of this function. So at x equals -1, right here, we have a minima of -2. At x equals 4, we have a minima of 0, the y value is 0. And at x equals 2, we have a maxima, that's the hill, of 3. So you're going to just find the x value and the y value of the hills and valleys. Okay, now looking at this is a cube function. This here really doesn't ever go up or down. It's just sort of a flat S-curve through there. So there's no maximum, there's no minimum, there's what we call an inflection point. It just takes a turn through there, but it doesn't really go up or down to make a hill or a valley. So it can have several hills, it can have several maxima, it can have several minima, it can have one, none. You just have to look at the graph and determine that. Okay, so determine the relative maxima and minima. So we have a maxima here at x equals 2. And so if they want to list it as at x equals 2, negative 2, the maximum is at 3, or it's at the point negative 2, 3. All right. At x equals 2, we have a minimum, relative minimum, at 0. So at the point 2, 0, there is a minimum. Okay? All right, that's the end of this. Watch some of those other videos if you think it will help you, and work on your homework.